Just a second, please.
Yes.
Just give us 1 second. Okay, I also want to mention that the format is 25 minutes talk and 5 minutes for questions. So I'm going to give you a warning 3 minutes before your 25 minutes are over.
Okay, thank you. Okay, so I'd like to thank the organizers for giving me this opportunity to give a talk online. This work is based on collaboration with these people. The numerical sign problem is one of the major obstacles when performing first principles calculations in various fields of physics, including finite density QCD, quantum Monte Carlo simulations of quantum statistical systems, theta vacuum with finite theta, and the real-time dynamics of quantum fields. Today, I'd like to show that a new algorithm we proposed, which we call temporal-Lefschetz thimble method, or shortly TLTM, and its extension, world volume TLTM, or WV-TLTM, may be a promising method towards solving the sign problem by exemplifying its effectiveness for various models, like this. And I also would like to discuss the computational scaling of this method. Okay, now so let me set up the, define the problem. Okay, our main concern is to estimate the expectation value of some physical observable. Here, x is a real valued dynamic variable, and Sx is the action. And if Sx is the action is real valued, then one can regard the Boltzmann weight as a probability distribution function with this property. So we design a Markov chain to generate a sample like this, which obeys this distribution. Okay, and here nconf is the sample size. And if it may be confusing, okay, here n is the degrees of freedom, but nconf is the sample size. Okay, and then the expectation value is estimated by this numerical average, sample average. Okay, but when the action is complex valued, one can no longer regard this Boltzmann weight as a probability distribution function. Then the most naive method is a so-called rating method, where we decompose the action to the real part and the imaginary part like this, and use this factor, as a new Boltzmann weight. Okay, then the expression value can be written as a ratio of these reweighted integrals, and here the phase part is absorbed in the operator part like this. So this is a ratio of the expression value with this new Boltzmann weight. So, but when the degrees of freedom is very large, then each of the numerator and the denominator is a very small number of this form. Okay, and it does not cause a problem if we can estimate the numerator and the denominator precisely to give some order 1 quantity. But in the numerical simulation, we have these statistical errors like this. Okay, so in order for these statistical errors to be regarded as small quantities compared to this main part, then the degrees of freedom must be we need to have this inequality, which means that the sample size must be very huge. Okay, so which means that the computational time must be very, very large, which is actually the sign problem. Okay, let me explain this sign problem for a very simple example, which is Gaussian. Okay, so the action is given by this, and for this case, the real part is given by this, and the imaginary part is given by this. Anyway, the essence is that the action takes a very large value. So here the large beta mimics large degrees of freedom. And we take x squared as an operator. Then the expression value is expressed by this ratio of related averages. And because this is simply Gaussian, so one can exactly estimate the numerator and the denominator to take this value. And you see that each has a very small value, okay? But in the numerical computation, you have this statistical error. So in order for this to be small, then we need to have this inequality, which means that the sample size must be very large of this size. Okay. The mathematical essence of this small number is the following. Okay. Here, okay, we have the very large coefficient in the action, which means that so the real part and the imaginary part both have this large beta in the expressions, but the real part defines the distribution. So the width of the distribution is given by 1 over square root beta, but for the oscillation, the width or the period is given by 1 over beta. So if beta is very large, then this width can be much smaller than this width of distribution. So the integration becomes very highly oscillatory. And this is a reason why we have such small numbers in these expressions. There will be proposed various approaches to the sign problem listed here. And Jun Nishimura-san's talk in this session will be related to this complex Langevin method. But in my talk, I'd like to focus on this Lefschetz thimble method. And okay, so I start from the review of this Lefschetz thimble method, then explain its tempered version and also its word volume extension. So this is the plan of my talk. So I just finished the introduction, and I explain these methods, and then apply our method to various models like this. And finally, I'd like to conclude my talk with some outlook. Okay, the basic idea of the thimble method is to complexify the dynamical variable. Okay, here x is a real value, the original one, but we extended or complexified this to the complex value z, living in a complex space c to the n. Okay, and we always assume that the Boltzmann weight and the physical observables are entire functions over the complex space. So then, thanks to Cauchy's theorem, integral does not change under continuous deformation of integration surface from the original surface to deformed surface sigma here. Okay. If we fix the boundary at infinity, then so this is the original expression of the expectation value, but this can be rewritten in this form. Here, sigma is the now new deformed integration surface. So even when there is a severe sign problem for the original surface, the problem will be significantly reduced if the imaginary part of the action is almost constant on this deformed surface. And the prescription for this deformation is the anti-holomorphic gradient flow given by this. This describes a flow starting from some point x on the original surface into the complex space like this. And this flow has this nice property that is which is expressed by this inequality, from which we see that the real part of the action always increases except at the critical point. Here, a critical point is a point where the gradient of the action vanishes. Okay, and actually this corresponds to a saddle point for one-dimensional case. And also we see that the imaginary part is constant is always constant along the flow. So if we define, if we define a Lefschetz thimble J, which is which consists of orbits starting from some critical point, this critical point zeta, okay, then by this construction and this property, the imaginary part of the action is constant on this surface, on this Lefschetz thimble, okay, and if the surface approaches to some Lefschetz thimble with some critical point, then the imaginary part of the action should be almost constant if flow time t is very large. So we expect that the sign problem disappears on sigma t if we take a sufficiently large flow time t. Okay, let me explain how the sign problem disappears. Okay, so let me remind you that, so the original sign problem, it was like this. So we consider the integration on the original surface with the weighting method with this oscillatory factor, okay? And so this gives a very small main part with these statistical errors. So we need a huge size of sample, which is the origin of the sign problem, okay? And but after the flow, one can show that the integration on a deformed surface will have this expression for the main part, okay? So in the exponents, there is this damping factor, okay? Here, lambda is a typical singular value of Hessian, defined by this. So if flow time is sufficiently large, actually, if t is greater than the logarithm of the degrees of freedom, then these main parts are now all of order 1. So there disappears a small number in this expression. So the sign problem disappears at flow time t, which is the logarithm of the degrees of freedom. Let us check this for the simplest example, Gaussian case. Okay, so the action was again given by this. And in this case, the flow equation is just a linear equation, so it can be solved very easily to obtain this, okay? Then the real part and the imaginary part have this form. And please note that the real part increases actually with this exponential factor. On the other hand, the imaginary part does not change along the flow, okay? So if we use this expression to calculate the ratio of the weighted average, then we have this expression, okay? So due to the existence of this small, this large factor, now this numerator and the denominator each has this small, okay, so this order 1 variable if t was taken sufficiently large to satisfy this inequality. So mathematically, what happens is, okay, we know that the imaginary part does not change, so the width or the period of oscillation does not change. But due to the increase of this factor, then the width of the distribution shrunk exponentially like this. So if you take the flow time very large, then as I say, the oscillator integral disappears. So this is why the sign problem is solved in this method. So far so good, but this is not the end of the story. Actually, there comes out another problem at large flow time t. This is an ergodicity problem. So let's consider this action given by this Boltzmann weight. Okay. For this case, there are two critical points and correspondingly to Lefschetz thimbles. But in addition to this, we have a zero of the Boltzmann factor, where the real part of the action diverges. Okay. So we would like to make some, Monte Carlo calculation on this sigma t, but But there appears an ergodicity problem because these two configurations cannot communicate with each other easily due to the existence of this infinitely high potential barrier. And the solution we proposed some years ago is to implement the tempering algorithm to the thimble method by using the flow time as a tempering parameter. And okay, so the algorithm is given by this. Okay, so we introduce replicas in between the original integrating surface sigma naught and the target deformed surface sigma t, like this. Okay, so sigma t naught, we inserted sigma t1, sigma t2, blah 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 in between these two surfaces. And then we set up a Markov chain for this extended configuration space such that configurations can move easily along flow time direction. Then these two configurations can communicate with each other easily because they can bypass how to say they can bypass the how to say okay, they can make a bypass by passing through this a detour like this. Okay, so this prompts equilibration of the how to say stochastic or stochastic process on this sigma t. So after equilibration, we estimate the observables with a sample taken from this sigma t, the target deformed surface. So this algorithm solves the sign and ergodicity problems simultaneously. Okay, so let me skip this. Okay, and actually we applied this method to various models, and the results are always successful. But there are some drawbacks in this algorithm. So let me summarize good points and bad points of this algorithm. Okay, please recall that we insert a finite discrete set of replicas in between the original surface and the target surface sigma t here. So good point is that it can be applied to any systems once they are formulated by path integrals with continuous variables. Okay, but a drawback is its large computational cost. Actually, the necessary number of replicas increases like this, and also we need to calculate the Jacobian every time we exchange configurations between adjacent replicas. Okay. So to solve this problem, Matsumoto and I developed the word volume Monte Carlo, which we call word volume temporal-reflexive thimble method. So now which is a hybrid Monte Carlo algorithm on a continuous accumulation of integration surface, and we call this R, and we call this word volume by volume. Actually, we borrow terminology from string theory because this can be regarded as an orbit of integration surface in the target space C to the n. Okay. Then with this algorithm, in addition to this original good point, we can expect major reduction of computational cost because we no longer need to introduce replicas explicitly, and also because we no longer need to calculate Jacobian in each molecular dynamics process. And also configurations can move largely due to the use of hybrid Monte Carlo. Okay. And the basic idea behind this algorithm is the following. Okay, so this is the original expression for the expectation value, and as I told before several times, this can be rewritten to this form thanks to Cauchy's theorem. Okay, and here the numerator and the denominator, each of them is does not depend on t. So we can integrate each of them over T with an arbitrary weight. Okay. So anyway, so we just rewrite the expression as an integration over this world volume or over this region. Okay. And this is some, how to say, details on the algorithm, but I'd like to, let me skip this. So we applied this method to various models, and I'd like to focus on this two-dimensional Hubbard model and the Chiral and random matrix model. For the Hubbard model, we used the original temporal-Lefschetz thimble method. The Hubbard model is defined by this Hamiltonian. Here, C are creation and annihilation operators on site X and with spin sigma. Okay, and N is the number density, and kappa is a hopping parameter, and mu is a chemical potential, and U is the strength of on-site repulsive potential. Okay. And I have already shifted the number operator by 1/2 such that the vanishing chemical potential corresponds to the half filling state. Okay. Then the ground partition function. Then after high Bosnization or Hubbard sandwich transformation, the ground partition function can be written in the form of a path integral over a scalar field to phi. Okay. And we applied the temporal-Lefschetz thimble method to this system. This is a result, okay, for the number density, okay. The blue data are the results with the naive rating method, and we see that they disagree with exact values and also have large errors due to the sign problem. And these two data are obtained with simple method, but for the orange ones are data without the implementation of the thimble method, without the tempering. Okay, so you see that they deviate from the exact values, but with tempering, they agree with exact values. To see what happens, let us focus on this point. Okay. Okay, this is the distribution of flowed configurations at flow time t equal to 1/2. And here the flowed configurations are projected on a plane defined by this. So, and without tempering, we see that the flowed configurations are stuck to a small number of thimbles. Actually, this can be a single thimble in this case. And with tempering, you see that the flowed distributions are scattered widely over many thimbles. Okay, so this is why we actually could get a good result. Okay, let me skip this. Okay. Now, I'd like to talk about our application of the method.
Just to let you know, you have 3 more minutes.
Okay, thank you very much. Now the application of our method to a Chiral random matrix model, actually the Stefanov model. Okay. And we use the world volume version of TLTM. Okay. The final density QCD takes this form. Okay. And after the integration over the Fermi fields, we have this determinant and this expression. Okay. And the Chiral matrix model, especially Stefanov model, is obtained by replacing the gauge field, or more precisely, this covariant derivative by a matrix, a complex matrix of size n by m, like this. Okay. So the degrees of freedom is given by this formula, which corresponds to the lattice degrees of freedom. So here L is the linear size of a 4-dimensional lattice, and C is the color, and the color degrees of freedom. Sorry, the color. Okay. And and this model, this Stefanov model is a very important benchmark model because it well approximates the qualitative behavior of QCD at large matrix size, and also it is known that the complex Langevin method suffers from the long convergence problem for this model. And this is a result. Okay. Okay, so for the chiral condensate, okay, this is the result for the chiral condensate and the result for the baryon number density. And you see that the naive weighting method again gives wrong numbers with large statistical errors. But the temporal method gives correct results agreeing with exact values, while the complex Langevin method disagree with exact values due to the long convergence problem. Now here is okay, and we also measure the computational scaling for this model. Okay, and we use the direct method for the linear inversion. Okay, then this is a scaling of the computational cost. Okay, and the top line is a result obtained with CPUs, and the bottom line is the result obtained with CPUs and our GPU. Okay, and we calculate this on a supercomputer at Yuhma Institute. Then okay, so we clearly see that the computational scale is n cubed for generating. Actually, this is the computational cost to generate a single configuration. Okay, and this is actually reduced from the expected scaling with the original temporal thimble method. And the important point anyway is that the scaling is not exponential. This is power-like. Okay, so this shows that okay, so at least for this model and for this lattice size or for this degrees of freedom, sign problem is actually solved. And now we are changing the code for the linear inversion from a direct method, actually LU decomposition, to an iterative method by CG stub. Okay, and in this case, we no longer need to calculate the Jacobian in generating configuration. So we expect that this exponent will be significantly reduced. Okay, but we will see. Okay, so let me summarize my talk. Okay. Okay, so I have argued that the tempered Lefschetz thimble method has a potential to be a solution to the sign problem because it solves, and actually it solves the sign and ergodicity problems simultaneously. And I also demonstrated that the method has been successfully applied to various models, although the degrees of freedom is not so large at this stage. And the target of the application was toy models for these important targets. Okay. Okay. And as a future work, okay, we are now actually as a current work or as an ongoing work, we are now preparing the large-scale computation for large-site systems with this algorithm. But it is still important to improve or to further improve the algorithm itself. And also, I think that it is nice if we can combine this method, world TLTM, with some other algorithm, such as tensor normalization group method, which is a non-Monte Carlo algorithm, but it's good at calculating the partition function of free energy. And the particularly important target must be the Monte Carlo calculation for time-dependent systems. Actually, if one can do this, then the force principle calculation of non-equilibrium processes will be possible. Okay, that's all. Okay, thank you very much for your attention.
Thank you. Are there any questions? Maybe any online questions? Okay, then no more questions. So let's thank the speaker again.
Okay, thank you. So, okay. Okay, so let me.
So our next speaker is Jun Nishimura. Can you hear us?
Yes.
Okay, we hear you too. Could you share your slides? Okay. So the format is 25 minutes talk and 5 minutes questions. And I'll
Yes.
give you warning 3 minutes before your time is over.
Yeah. Okay.
Okay, please start.
Okay. So I would like to talk about this IKKT matrix model, which I have been working on for more than 20 years. But I think we start to see the goal of this project. So I would like to explain what it is. And as one of the organizers, I feel very sorry that I cannot be in Corfu this year, but I'm still very happy to talk about this project in this workshop. Okay, this talk is based on this paper on JHEP and also on this ongoing work done in collaboration, particularly with Costas, with there. Okay, and also Stratos is also there as well. Okay, so what is IKKT model? This is a model conjectured by these 4 Japanese gentlemen in 1996 as a conjecture, as a nonperturbative formulation of superstring theory. And it is made of 2 terms in the action. One is the bosonic term, and the other is the fermionic term. And A mu and psi are both Hermitian matrices, and mu is the Lorentz vector, and alpha here is Majorana-Weil spinor indices. And because of that, this action has SO91 Lorentz symmetry in 10 dimensions. And these mu indices are contracted by using Lorentzian metric eta. And well, if you make a weak rotation using this definition, redefinition of the matrices and the gamma matrices, you end up with an Euclidean version of the model, which has SO10 symmetry. And for most of the time, this Euclidean version has been studied. And let me show you perhaps the most important results for the Euclidean model. I mean, this paper we published recently, and a few more slides later. And before that, let me explain the crucial properties of this model as a nonperturbative formulation of string theory. First of all, one can see the connection to perturbative formulations of string theory by considering the worldsheet action and the light cone string field Hamiltonian. These things can be easily seen from the matrix model. And another point is that this model is expected to be a nonperturbative formulation of the unique theory underlying the web of string dualities, because now we know that, well, although the matrix model, this model is directly related to the type 2B superstring theory, now we know that all the different 6 types of string theory or M theory are related to each other by the so-called string dualities. So we expect that this model describes basically all of them. I mean, describes the unique theory underlying these dualities. And the third thing I would like to emphasize is that this model has 10-dimensional n equals 2 supersymmetry, which cannot be realized in quantum field theories without gravity. So if the low energy effective theory of this model is described indeed by quantum field theory, then it should inevitably include quantum gravity. This is a very strong statement, and I think it's very important. And if you look at the SUSY algebra realized in this model, you notice immediately that the translation is actually realized as a shift of the Hermitian matrices A mu by this term. And this suggests that the space-time is actually represented as the eigenvalue distribution of A mu. So the space-time is not there in this model a priori, but it actually emerges from the matrix degrees of freedom. So by studying the eigenvalue distribution of these A mu matrices, we can see what kind of space-time appears dynamically in this model. That is another important point. So as I said, I would like to briefly review what we obtained for the Euclidean IKKT model. And this is actually very concrete and robust results. So there should be no doubt about it. But then we would like to discuss the Lorentzian version of the model. And first of all, even the definition is not obvious, so let me discuss it. And then I will tell you how we investigate the model, the Lorentzian model, and then show you some results from our complex Langevin simulations. Then I would like to summarize. Okay, so the Euclidean model. As I said, the Euclidean version can be obtained by making this weak rotation. So A0 is replaced by minus IA10, where A10 is now considered as Hermitian matrix. Then the Bosniak part of the action becomes just trace F mu nu squared, where F mu nu is defined in this way in terms of the commutator of A mu and A nu. So obviously this is a positive semi-definite term. So the Euclidean model has this nice feature, but the Lorentzian version, you can easily see that, well, term with F0i, where I is spatial direction, becomes has an opposite sign. So the action is not semi-positive, semi-definite anymore. Now, if you consider this positive semi-definite action for the Euclidean model, you might be worried about the flat direction, because this action obviously has a flat direction corresponding to commuting matrices. But okay, so there are some important comments on this issue. First of all, if you consider the Bosniak version of the model, because of the quantum effects, this flat direction is lifted up. This was noticed a long time ago in a slightly different context. However, if you have supersymmetry, this will not occur. Namely, the flat direction will not be lifted, so it remains to be flat. So in the original IKKT paper, they noticed that this is the case. So they actually introduced some cutoff on the eigenvalues of A mu. However, soon later, these people noticed that actually if you consider the fermionic Zermos carefully, then this flat direction is lifted up. So in fact, even in the supersymmetric case, the Euclidean model is well defined without any cutoff, and this has been proven rigorously by these people. And actually, quite recently, we did some simulations, which is quite non-trivial because of the sign problem that was discussed by Masafumi in the previous talk. But we were able to overcome this problem by using complex Langevin simulation, which I'm going to talk about later. Anyway, this is the result we get for the Euclidean IKKT model. And I'm not going to tell you the details, but we are plotting basically the 10 eigenvalues of this so-called moment of inertia tensor in this model. And if you look at the 10 eigenvalues and see how they are split, you can tell what kind of symmetry the spacetime has. And for instance, in this case, you have SO7. In this case, you have SO4, and so on. And here, MF is the deformation parameter we have to introduce in order to make this complex logical method work in this model. And eventually, we have to send this MF to 0 to retrieve the original model. So as you see, MF, if you look at MF 3, 1.4, 1.0, and 0.9, as you go to smaller MF, the symmetry of the space becomes smaller, and it becomes SO3. So, of course, you might wonder whether it can go even further to SO2, for instance, but that doesn't seem to be the case. There is some analytic argument that that cannot happen. So our conclusion is that in this model, the SO10 symmetry of the Euclidean model is broken spontaneously to SO3. That is our conclusion. Okay, so that is the results for the Euclidean model, but how? Now the question is what we can say about the Lorentzian model. First of all, what is the partition function of the Lorentzian model? So let me explain that this is the natural definition. Here we inserted I, which doesn't exist for the Euclidean model. In the Euclidean model, we have exponential minus SP, for instance, for the bosonic model. And then this, well, you have a well-defined theory. But here in the Lorentzian model, it is natural to have I in front. And this can be understood by looking at the worldsheet action of the string theory. And here, the worldsheet action, you have these worldsheet coordinates, which includes time direction as well as the spatial direction. So when you make a weak rotation, it would be more natural to have one of the worldsheet coordinates to have minus I, and that will result in this I in front of the action. So we will take this definition, and then the Lorentzian model is not actually well defined as it is because of this I in front of the bosonic action. This term is just a pure phase factor. So there is no suppression when you go to large A mu. And this Pfaffian comes from integrating out the fermionic matrices, and it is just a polynomial in A. So once again, this does not have any suppression for large matrix elements. So in order to make this partition function well-defined, one thing we can do is to make a weak rotation for the worldsheet and the target space. So as I said, the matrix model action corresponds to the worldsheet action, and making a weak rotation on the worldsheet corresponds to putting some phase factor in front of the action, obviously. And now we should also make a weak rotation in the target space, but the target space is nothing but the matrices A0. This is the temporal matrix. So we have to put some phase factor in front of A0. So we have these two parameters, S and K, for the weak rotation. But this weak rotation is nothing but deforming the integration contour in the model. So here we have, well, we have this A0 and AI transformed into A0 tilde and AI tilde according to this weak rotation. But when we set this S and K to be the same, like U, then we have this phase factor for both temporal and spatial directions. So this is just the deformation of the integration contour, and U equals 0 corresponds to Lorentzian, and U equals 1 corresponds to Euclidean. Now, the important thing to notice here is that the positive formed theory is well defined for u larger than 0 and less than or equal to 1. And this can be seen easily because if you plug in this redefinition of the matrices and write down everything in terms of A tilde, you find that the action is still real positive. You have these factors has a positive real part if u is within this range. So that means that the model is well defined. So there is some subtlety, of course, at the Lorentzian, exactly Lorentzian point, which corresponds to u equals 0. But of course, you can define the theory at non-zero u and take the u going to 0 limit to define the Lorentzian model. That is, of course, possible. And if you do that, because of the Cauchy's theorem, all the correlation functions can be calculated using the Euclidean model. All you have to do is just to redefine the matrices in this way, and then you get all the results for the Lorentzian model. So in that sense, the Lorentzian model is equivalent to the Euclidean model if you use this deformation of the integration contour. And we can actually confirm this equivalence by doing explicit complex Langevin simulations. We did it for the 10-dimensional bosonic model. And these are the expected relationship between the Lorentzian model and the Euclidean model. These are the results of the complex Langevin simulations, Euclidean model and the Lorentzian model. They have the same magnitude, but different in the phase. And this phase is precisely in agreement with what we expect. Okay, that's good. But then the emergent space-time in the Lorentzian model should be actually interpreted as being Euclidean because of this equivalence. And if you look at the Euclidean model correlation function, this, for instance, this correlation function is real positive. And this is nothing but the temporal extent, and this is nothing but the spatial extent. They are both real positive in the Euclidean model, but if you consider the corresponding correlation function in the Lorentzian model, they have a strange phase factor. So if you consider the Lorentzian model as your model of interest, the space-time that emerges there is actually Euclidean, not the real space-time. So we would like to do something. We would like to, well, say, introduce some boundary condition to solve, well, overcome this situation. So how should we investigate the model? So this is the method that we are using, the complex Langevin method. And I don't have the time to explain the detail, but let me just tell you what we are doing. We have the effective action. Well, alpha and tau will be explained later, but anyway, we are solving the complex Langevin equation. This is a fictitious time, and by solving this equation, and this eta here are Gaussian noise. This is a stochastic differential equation, and we can solve it numerically, and then we can calculate various correlation functions. And the important point to note here is that all the dynamical variables should be complexified, as in the case of the previous talk. And in this work, we omit the fermionic matrices and focus on the bosonic model. So how do we define time in the IKKT model when we do complex Langevin simulation? This was also discussed in this paper. First of all, we fix the UN symmetry, which is nothing but this symmetry of the IKKT model. And we do this gauge gauge fixing by making this A0 temporal matrix to have this diagonal form with this ordering of the diagonal elements. And if you do that, you have this fundamental determinant coming out because of the Padef-Popov of the determinant of this gauge fixing. And then in order to realize this ordering of the diagonal elements, we make a change of variables from alpha to tau, where tau is at this point still a real variable. Obviously, if you write everything in terms of tau, this ordering of alpha is satisfied. But then we can complexify all the variables, so tau will be complexified. It is not real anymore in the simulation. And alpha becomes complex as well. And also the spatial matrices AI becomes complex when we do complex Lagrange simulation. And then we can look at the expectation values of the time coordinates, which we call alpha. And in the Lorentzian model, it is related to alpha tilde in the Euclidean model. And as I said, we have this phase factor. So in the Lorentzian model, time is complex and it has this strange phase factor. But in order to make the real time to emerge, we introduce a constraint like this on alpha. These are the two ends of the these eigenvalues of A0, right? So alpha n and alpha 1, the difference is fixed to be some complex number that we wish to fine-tune in such a way that the eigenvalues, namely alphas, lie on the complex plane like this, where at both ends it becomes parallel to the real axis. And that means that you obtain a real time at both ends of the spectrum. So here we have a Euclidean-like region because you have a phase factor, this phase factor, but at both ends of the spectrum you don't have the phase anymore, it becomes real. So we have the Lorentzian regime. So this is very nice. We have, well, Euclidean regime as well as Lorentzian regime. So it implies a signature change. But now so far we have been talking about the time, but what about the space? So in order to extract the time evolution of the space from the Lorentzian model, we use this proposal we did in, well, almost 10 years ago. Namely, when we diagonalize A0, AR, AI have this kind of, well, bound diagonal structure. And this is a result that we obtain by Monte Carlo simulation. This is a non-trivial dynamical property, but since this is the case, we can, well, extract some block matrix here from the spatial matrix and define it as the state of the universe at the time, which is defined as an average of the eigenvalues of A0 within the same block. So in this way, we can define the time evolution of the space, namely this matrix, block matrix represents the state of the universe at time t. And then we can try to look at how the extent of space evolves with time. But no, please note here that once again, if you calculate this quantity, which is supposed to be the extent of space, it is actually not real positive in the Lorentzian model. But of course, if you introduce some constraint like this, the equivalence to the Euclidean model is no more true. So in principle, you can have some region where this quantity is Euclidean, whereas it becomes real positive in some other region. That is possible, and we are trying to look for such a phenomenon. If that is realized in this model, it means that the signature of the space-times can change dynamically in the IKKT model. And let me show you the result. This is the result I showed you already. And as you see, if you look at the eigenvalues of the temporal matrix A0, it has this Euclidean region, but it also has this Lorentzian region. So we can have some real time at both ends of the spectrum. But if you look at the time evolution of space, this is the result. This quantity, the extent of space, if you take the absolute value, it has this nice time dependence. So it starts off at some small number, but it seems to increase towards the future and the past. So it looks like this is a bouncing universe scenario. But if you look at the phase factor of this quantity, the extent of space, you notice that it is still non-zero, something like this, pi/8, which is actually the phase factor you obtain from the equivalence to the Euclidean model. So unfortunately, so far, the space is still Euclidean-like, but we expect that if we extend the time direction further, then eventually the real space emerges. That corresponds to having no phase. This phase factor becomes just 1 in the late time. That is what we expect.
Sorry to interrupt, just to let you know you have about 2 minutes.
Okay, thank you. So let me summarize. So I discussed the IKKT model as a nonperturbative formulation of superstring theory. The Euclidean model is well studied already, and it exhibits SSP of SO10 to SO3, which is, of course, very interesting. And this occurs due to the phase of the fermion determinant, or Pfaffian. And in fact, the Lorentzian model is equivalent to Euclidean model if we define it by the formation of the integration contour. So that means that the emergent space-time in the Lorentzian model is actually Euclidean-like. So in order to overcome this situation, we propose to introduce a boundary condition on both ends of the eigenvalue spectrum of A0, and then the signature change from Euclidean to Lorentzian may naturally occur. And our results so far seems to suggest a kind of bouncing universe scenario, unlike Hartle-Hawking's no boundary proposal. So in the sense that you have Euclidean space-time at the beginning of the universe, it is, well, looks like similar to Hartle-Hawking, but the fact that we have some kind of bouncing is slightly different. And the question is whether we can make the duration of the real-time regime longer by the boundary condition at large n. And another question is whether the space becomes real at late times and whether the expanding behavior like inflation show up. And this is the result of the classical equation of motion that we obtain in this paper. If you look at it, the space-time indeed, space indeed expands as you go to future and the past. So we expect to see similar behavior also in the complex Langevin simulation. And in this talk, I didn't explain anything about the fermionic matrices, but if you do that in this Lorentzian model, we expect that SSP occurs also in the Lorentzian model with the boundary conditions. And since we have a Euclidean regime at the t=0, we expect that the results of the Euclidean model, that SO10 symmetry is broken to SO3, is somehow realized also in the Lorentzian model in the Euclidean regime, and that might be the reason why we are living in 3+1 dimensional universe. Okay, that's it. Thank you very much.
Thank you. So, any questions?
Hello. I want to make some remarks. So I was in 90 in conference dedicated to Sakharov. It was 1990. So they distributed the publication of Sakharov, and I was amazed to see the article, which was dynamical change of signature of metric change. So he was considering dynamical transitions from Euclidean to Lorentz and back. So I like your picture where you show that it is some here you also have yes, that's the graphic where you see that there is a dynamical transition from Lorentz to Euclidean. So maybe it will be interesting to you to find this article. It was published, I think that it was Успехи физических наук in Russian, UFN, and 90 some at that time. You can find his article. Thank you.
Okay. Yeah, thank you for your comment. Yes.
Happy more.
Yeah, I have some doubts about the definition and the meaning of the initial partition function for the Lorentzian model. I understand the partition function. Is it the result of some evolution operator? In which case I would understand the I in front. But then you need some external time parameter with respect to which you define the evolution operator. If it is a Euclidean or a statistical partition function for Lorentzian matrices, then I really see why it should ever be an I in front of the exponent.
Yeah. Yeah, of course, this is not obvious. I mean, we spend a lot of time in figuring out what is the correct partition function. But one way to look at this is to consider, if you consider the real, the quantum mechanical system and try to consider the real-time evolution. And then, of course, you have exponential IS over H bar. So this partition function is something similar to that.
No, you have an evolution operator in that case because you have an external time direction. It's not a matter of being quantum or classical. You can have quantum statistical mechanics in which you have equilibrium partition function. Everything is quantum, but you have a minus in front of the exponent because it's equilibrium. There's no external time evolution.
So what is your proposal? So you're going to replace I by just -1?
The only way in which I can understand the partition function in absence of space-time is in the quantum statistical mechanics. Indeed, any notion of time evolution should be the result of the dynamical degrees of freedom you're integrating over. But the Lorentzian Euclidean should come from the dynamical degrees of freedom that is using Lorentzian or Euclidean matrices, not by the exponent being with an I or with a minus.
Okay, we have one more question.
Yes, okay. Let me think about that. Okay, please.
We also have online questions.
So,
hi, Jun, this is Howard.
hi.
I wanted to ask briefly, so the way you impose these particular asymptotic boundary conditions, so then you sort of see that at the end of your simulations, maybe you're entering the Lorentzian regime. Now, of course, it would be extremely useful to make contact with some perturbative computations, which are sort of focused on some irreducible configuration. In terms of, I don't know, by changing these conditions in some way, that's somehow to focus on these regimes, because in the present approach, it seems very hard to make contact with perturbative considerations.
Well, I'm not particularly interested in making connections to perturbative calculations. I'm just trying to define the real time in this model. I mean, because if we don't do anything, it just becomes complex. I mean, you see this identity, right? So we have to do something. We have to introduce some constraint or whatever. You have to change the definition somehow. So this is the minimal thing that we can think of when we want to get some real time at late times. So of course, there might be other possibilities, but this is the simplest thing that we can think of so far.
We have 2 more questions online.
Yes, please.
Yeah. Hello. This is Frans Klinkhamer.
Oh, hi, Frans.
Now, Jun, I can hear you. So very nice talk. I understand a little bit better what you want to do, but
Yeah.
we don't have time to discuss all that. So just a question about a remark about the interpretation all the way at the end. You talk about a bouncing universe, right?
Yes, yes.
And that you should, I think, qualify, because whatever you get, you have something on the horizontal axis that is a coordinate. And what the coordinate means physically is not clear. So it can very well be that there is a null phase at your, what you call t is 0, which physically generates a universe for positive coordinate t and an anti-universe for negative coordinate t, you see? So, and that is actually supported by results looking at what I had this regularized metric at the perturbations. Namely, the thermodynamic time is the time that goes in the direction of growing perturbations. And then it could very well be that what this model generates, this is also what I now think, is something like a universe anti-universe pair.
Yeah. Well, all I can say is, well, of course, there is a Z2 symmetry in the model. So this behavior is just reflecting that symmetry.
No, but your results are not exactly symmetric around t is 0 in your figure.
Oh, well, this is just a snapshot. So if you take an average over ensemble, then you get perfectly
Still,
symmetric
this can be
result.
perfectly, this comes from CPT invariance. And so I tell you that it don't hang on the word bouncing universe.
Yeah, okay.
Something comes out, and how that is to be interpreted physically, that remains to be seen by the matter. Namely, you also generate matter.
Sure.
Okay, but anyway, nice talk.
More questions.
Okay.
Hello, can you hear me, Jun?
Hi, Toby.
Hi, it's Toby.
Yes.
Hi, very nice talk. Thank you. I was just wondering, this interesting constraint you place on the eigenvalues. I wonder, just thinking about normal semi-classical gravity, if you had, say, a cosmological constant and you were thinking about what the gravitational partition function is dominated by, then, you know, going back to Euclidean gravity, people would say, well, it's dominated by the Euclidean sphere. But then Hawking said in various papers, you know, if you want to calculate what's the probability of living in a universe with a particular Hubble constant, you then have to evaluate the sort of wave function of the universe, which comes from the path integral with a constraint that the Hubble constant takes the value you want. And so I wonder if that's what this, you know, in some sense, this constraint may be allowing you to calculate a wave function or a probability for a universe with some particular behavior. And so if you don't put in the constraint, maybe it just wants to give you a Euclidean sort of saddle point. But if you want to ask if we live in a universe with a particular, you know, Lorentzian behavior, what's the probability of that universe? It's just a thought.
Yeah, okay, thank you very much. Yeah, it's a very nice interpretation of what we're doing. Yes, I have to think about it. Yes, very nice.
Thank you.
Okay, if there are no more questions, let's thank the speaker again.
Thank you.
So our next speaker is Asato Tsuchiya. Can you hear us?
Yes.
Okay. So could you please share the slides with us?
Yes.
Okay, so the format is 25 minutes talk and 5 minutes for questions. I'll give you a warning 3 minutes before the time is over.
Yes. Okay, so can you see my slide? Okay, can you hear me?
Yes, we can hear you.
Okay, okay. Okay, okay, okay. So, okay, let me start. Okay, so, okay, so thank you for introduction. And first of all, I'd like to thank the organizers for kind invitation. I hope to participate physically next time. And this talk is based on collaboration with Kazushi Yamashiro, my student. In this talk, I'd like to discuss a possible unification between two concepts which are expected to play a crucial role in constructing quantum gravity. One is emergence of spacetime, the other is quantum entanglement. So let me first point out that you can consider two types of entanglement entropy in field theory. In these figures, a horizontal plane represents the base space of field theory, while the vertical axis represents the configuration space of field, namely target space. So you can define the base space entanglement entropy by dividing the base space into subregion A and its complement A. While you can also define the target space entanglement entropy by dividing the target space into subregion A and its complement. Now, the most well-known example of connection between quantum entanglement and geometry is given by Liu-Takayagi formula in the ADS-CFT correspondence. The formula is here. The left-hand side is base space entanglement entropy in dual conformal field theory on the boundary, where A is the subregion on the boundary. And the right-hand side is proportional to minimal surface in the bulk, which is ADS spacetime. The boundary area of minimal surface. So the boundary of this minimal surface agree with that of subregion A on the boundary. This formula relates the quantum entanglement to geometry. So this is powerful formula, but in order to use the Liu-Takayagi formula, we need boundary space where dual field theory lives. So we have a following question. How can we use quantum entanglement to understand quantum gravity in space-time without boundary space? It seems natural to consider entanglement entropy in bulk. But we have difficulties such as division of dynamical space in quantum gravity. Now it is possible to define entanglement entropy in bulk spacetime as target space entanglement entropy in matrix models, where bulk space is given by target space of matrix models. In the matrix models, space or spacetime does not exist a priori, but emerges from the degrees of freedom of matrices. More concretely, space where eigenvalues of matrices live correspond to target space of matrix model. So what we will discuss in this talk is as follows. In order to draw a lesson on connection between target space entanglement entropy and bulk geometry, we consider a complex matrix model whose target space can be viewed as giving part of bubbling geometry developed by Lin, Luning, Maldacena. Target space in this case is two-dimensional plane where eigenvalues of this complex matrix distribute. So we calculate target space entanglement entropy in the complex matrix model and find that it follows an area law in the bubbling geometry. So the plan of the present talk is the following. In the next section, we will briefly review the target space entanglement. In section 3, we will review the bubbling geometry and complex matrix model. In section 4, we calculate the target space entanglement entropy in the complex matrix model. In section 5, we will calculate the area of entangling surface in bubbling geometry and compare the result with target space entanglement entropy in section 4. In section 6, we conclude. So we are going to review the target space entanglement entropy. Before that, let us recall the definition of base space entanglement entropy. We divide the base space into the subregion A and its complement, A bar. Then the total Hilbert space takes this tensor product form. So you can define the reduced density matrix rho A for the subregion A by taking the trace of the total density matrix rho over this Hilbert space HA bar. Then the entanglement entropy for the subregion A is given by the von Neumann entropy for the reduced density matrix rho A. So now let us consider the target space entanglement entropy. We divide the target space into the subregion A and its complement A bar. So in this case, the total Hilbert space takes this form, where we have summation over sectors labeled by K, integer K. This is not a simple tensor product. So it is complicated to define the reduced density matrix rho A, but you can do that. The result is here. Now, PK is the probability for realization of the kth sector. Then the entanglement entropy for the subregion A is given again by von Neumann entropy for the reduced density matrix rho A. It turns out that it takes this form. The first term corresponds to classical contribution, while the second term corresponds to quantum contribution. Okay, so as an example, let us consider n identical fermions in quantum mechanics. In this case, the target space is nothing but the space where these fermions live. So this figure shows the case in which the target space is one-dimensional. If we assume that these fermions are not interacting each other, the wave function is given by the Slater determinant as follows, where a chi-I is a wave function for a single particle. Now we consider the subregion A in the target space. Then we define the overlap matrix by this equation, where we have an integration over subregion A here. We denote the eigenvalues of this matrix by lambda K. Then target space entanglement entropy for this subregion is given by this formula. We have a summation over the sectors labeled by K. K in this case is the number of particles existing in the subregion A. H is Shannon entropy for Bernoulli process. Okay, so now we are going to review the bubbling geometry and complex matrix model. So the general form of half BPS solution that preserves R cross SO4 cross SO4 symmetry in type 2B supergravity is found by Lin, Lunin, and Maldacena. This solution is called LLM solution. This solution is fixed by specifying droplet on two-dimensional plane as boundary condition. On the other hand, in N equal 4 superimage theory, this solution corresponds to chiral primary operator, which is multi-trace operator of complex scalar field as follows, where capital Z is a linear combination of two scalars out of 6 scalars in N equal 4 superimage theory. And the dynamics of this chiral primary operator can be described by complex matrix model, which is obtained by dimensionally reducing the free part of the action for the complex scalar field capital Z. And these droplets correspond to eigenvalue distribution of complex matrix Z, capital Z. Now, the action of the complex matrix we study is here. This action is obtained by dimensionally reducing the free part of the action for the complex field Z on R cross S3 to R, that on R. Now, capital Z is N by N complex matrix depending on the time. Then the chiral primary operators in N equal 4 superimage theory can be described by the holomorphic sector of this matrix model. So the wave function for the holomorphic sector is given by this type of Slater determinant, where Z1.Zn are eigenvalues of the matrix Z. And actually, we decompose the matrix, complex matrix Z into this form, where U is a unitary matrix, and this matrix is upper triangle. So there are eigenvalues here, and this is non-trivial component. There are non-trivial components here. So we can integrate out the degrees of freedom of this matrix, expect these eigenvalues. So we can reduce the dynamics of this model to the dynamics of these eigenvalues. So the function phi L is in this Slater determinant is a wave function for single particle, which is given by the wave function for the lowest Landau level. This takes this form. So, and the energy level is labeled by the non-negative integer L. So in this way, this system can be viewed as n fermions on two-dimensional plane. This plane is nothing but the target space of the complex matrix model, where the complex eigenvalues live. Okay, so now we can consider various states in the complex matrix model. This is the ground state, which correspond to ADS5 cross S5 in the bubbling geometry. So we can draw the eigenvalue distribution for this state in the complex plane, like this. The ground states correspond to this droplet, where R naught is given by square root of n. And we can also consider the excited states here a particle excited. The excited energy is n minus 1 plus j here. And corresponding droplet is given here. So the R1, the radius of the outer circle is given by square root of n plus j. And we can also define, consider the excited states. Okay, so this excited states correspond to D3 brane left on S3 in ADS5, which is called ADS giant gravity. So we can also another excited state, which correspond to D3 brane left on S3 in S5, which is called giant graviton. This state is a sort of whole state. There is a hole here, and this radius R minus 1 is given by square root of k. K is here. Okay. So, okay, let us see what is bubbling geometry by LLM is like. The general form of half VPS solution preserving this symmetry R cross SO4 plus SO4 in type 2B supergravity is given by these equations. So the point is that this metric is determined by a single function z, which obeys the differential equation here. So the solution of this differential equation is fixed by specifying the boundary condition on the y equal to 0 plane. So the value of z on this y equal to 0 plane can take two values, 1/2 or -1/2. We assign white to the region in which z takes 1/2, and we assign black to the region in which z takes -1/2. So in this way, we obtain droplets on the y equal 0 plane as a boundary condition. Namely, if we specify the droplet on the y equal 0 plane, we obtain a solution of this type. And this geometry corresponds to ADS5 plus S5. So the droplet takes this form, and ADS giant graviton has this droplet, and giant graviton has this droplet. So the shape of these droplets agree with eigenvalue distribution in the complex matrix model. Okay, so now let us calculate the target space entanglement entropy in the matrix model. We start with a ground state. We consider the region, subregion A, which is a disk centered at the origin with radius R. So this red circle corresponds to the boundary of the subregion A. So now we calculate the entanglement entropy for ground states corresponding to ADS5 plus S5 in the bubbling geometry. It's given by this formula. Okay. So in this case, the overlap matrix is diagonal from the beginning, and the eigenvalues is given by the incomplete gamma function. So this figure shows the entanglement entropy against R. So you see that this is proportional to R in this region. R naught is a radius of the droplet. And you see that it suddenly dumps at R equal to R naught here. So this can be considered as finite end effect. And actually, this the boundary of subregion A is outside the droplet, then the entanglement entropy vanishes. So now let us consider the excited state corresponding to ADS giant gravity. The droplet is here. So now we take n equal to 25 and n plus j to 50, which means R naught is 5 and R1 is this value. So this is a entanglement entropy for this excited state. You again see that dumping at R equal R naught, and you also see the peak at R equal to R1, which is a radius of outer circle. So now we subtract the contribution of ground states from this entanglement entropy of this excited state. The result is here. This subtracted entanglement entropy for this excited state has peak at R equal R1 and vanishes in other regions. Okay, so now let's move on to the bubbling geometry. So we calculate circumference of boundary of A in y equals 0 plane by using a metric of bubbling geometry. So the length of this boundary is considered as area of entangling surface. So this area, so this figure shows area against R. So it's proportional to here, proportional to R in this region. And okay, so this is a area for ground states. Ground states correspond to ADS 5 and this figure shows the area for ADS giant gravity. So now we also draw contribution from ADS 5 here, this orange line. Then we subtract this orange contribution from the area for the ADS giant gravity. The result is here. Okay, so you see that there is a peak at R equal to R1, and it vanishes. So subtracted area vanishes in other region. This behavior agrees with the entanglement entropy for this excited state correspond to ADS giant graviton in the complex matrix model.
Sorry to interrupt, just to let you know there are 2 more minutes.
Okay, thank you. So now we can calculate we can consider the giant graviton in complex matrix model and bubbling geometry. So the droplet is here, and the entanglement entropy behaves like this. So we subtract the contribution of ground states, and the subtracted entanglement entropy behaves like this. You see that the peak at R equal R minus 1, but it takes negative value. But this sign should be flipped when we compare the result with area in bubbling geometry, because we regard hole as particle, namely D3 brane in the bubbling geometry. So now we have a shape like this. So now the area for giant graviton in the LLM geometry is given here. The orange line correspond to the contribution for ADS5 versus 5. We subtract this contribution. The result is here. So you see the same behavior of this subtracted area as the subtracted entanglement entropy in the complex matrix model. So now let me conclude. So we calculated the target space entanglement entropy for wave function in the complex matrix model that correspond to LLM bubbling solutions. The entanglement entropy for ground state is proportional to R in which correspond to area law. We also see the finite end effect. Next, we find an area law in the bubbling geometry, namely the behavior of target space entanglement entropy for ADS giant or giant graviton agrees with the area of entangling surface in LLM bubbling geometry. But this agreement is qualitative. So in order to gain quantitative agreement, we need a more elaborated correspondence between states and droplets. We also need to identify the effective Newton constant, because we expect to have formula like this eventually, where Gn is effective Newton constant. So we might have to consider the finite n effect in the bubbling geometry and complex matrix. So the afterlife is here. So we expect to see connection of our result to non-commutative geometry through Chern-Simon matrix model, which describes quantum Hall effect. We want to apply the target space entanglement entropy to study of entanglement entropy in fuzzy space, such as fuzzy spheres, fuzzy disks, and so on. So finally, we'd like to study target space entanglement entropy in BFSS model or type 2B matrix model to gain some insight into the connection between targets entanglement, quantum entanglement, and quantum geometry. Okay, that's all. Thank you for your attention.
Thank you. Any questions? Any online questions?
Can I ask a question?
Yeah, yes. Yes.
Yes. Maybe I missed something, but in the case of giant graviton, the peak went in the wrong direction for the two cases.
Yes, yes.
Is it a contradiction or is it okay?
We think it's okay. Yeah, this is a contribution of Hall.
Yeah.
But okay. So in the second quantized picture, this entanglement entropy has a positive peak. So we think this is consistent.
Okay, I see. Okay, thank you.
Thank you.
Any other questions?
Yeah. Hello, Frans Klinkhamer here. So I think this is very interesting, even for the 2B matrix model, because, you know, I've been looking at this master field. And in the end, I also get a complex matrix. And the question was, how do you get space-time out of it? And I had also thought a little bit about EE, but you have gone much farther. So I think so for the 2B matrix model, it is information, right? And the information may be encoded in the matrix model master field, and that is complex, right? And so this is very interesting. We should discuss, but we're not there together over a glass of wine. This is the problem, right?
Okay. Thank you for your comment. Thank you very much.
One more question.
Hi, Tsuchiya-san. This is Masanori.
Hi.
You mentioned the distinction between dividing the base space and dividing the target space. At the same time, you had a really nice series of papers in which space is encoded into matrix. So I wonder, from that picture, you can kind of unify 2 points of view or not? Like using a multiple sphere solutions, that you could show that the matrix model can regularize four-dimensional super-MLs.
Four-dimensional super-MLs.
Yeah, and so you encoded like a three-dimensional space to matrix. Now, so separating a target space and separating a base space, they look exact same there. So I wonder if you can see some sort of unification of the approach.
I think that is possible. So your talk is, I think your talk is related to.
Not that level yet, but yeah, I thought at the same time, I thought maybe such a point of view can be used to test whether your approach in a target space is good or not. That's what I vaguely thought.
I think eventually we can interpret. Okay, so we can interpret the target space entanglement entropy of N4 super-M theory as bulk entanglement entropy in ADS5 process 5. Okay.
Okay, so if there are no more questions, let's thank the speaker again. The last speaker for this session is Yuhma Asano. Can you hear us?
Yes, I am.
We cannot hear you.
Oh, really?
Okay.
All right.
Okay, so the format is 25 minutes talk and 5 minutes for questions. I'll give you a warning 3 minutes before the time is over. Okay, you may start.
All right, thank you very much. Well, thank you very much for the invitation. And well, I wish I were in Corfu, where well, beautiful scenery and tasty food, cheerful people are there. Well, but today, I'd like to talk about some real-time dynamics of the matrix model. But well, here I need to be well, honest about my talk, because in this talk, I'm not gonna give well, amazing results of real-time dynamics. So mostly this talk is about well, how I see the problems and outlook of this project. So the title is, well, I like to put towards numerical simulation of real-time dynamics of the matrix model. Okay, so well, I'd like to begin with the problems in string theory. In string theory, nonperturbative formulation is one of the main important problems. And well, as you all know, string theory is constructed based on the perturbation theory, so that we cannot compute non-perturbative physics from perturbative string theory. So for example, our universe, it's 4 dimensions. So, but in the current established string theory, there are almost infinitely many vacua, which has 4 dimensions. So there is no way to determine the true vacuum in the current established string theory. So in order to make string theory predictable, quantum gravity theory, we need non-perturbative formulation. And well, this picture is just for to depict what I said. This curve is corresponding to the effective potential, or I should have called landscape of string theory. And if we consider the established string theory, we well, the theory is around vacuum, each vacuum, but we cannot. But this curve of the effective potential should be extracted from after we define the non-perturbative formulation of string theory. So as a promising non-perturbative formulation, let's consider and focus on the matrix model. And I listed a matrix model, 3 matrix models here. So the first one is the original matrix model, which the first one to be considered in this context. And this is for bosonic to the string theory. And these two correspond to superstring theories, and the BFSS matrix model has 1 dimension, Yamio's theory, and the IKKT model has 0-dimensional Yamio's super-Yamio's theory. And these two matrix models, BFSS and IKKT models, can be obtained by dimensional reduction of n equals 4 super-Yamio's theory, 4-dimensional super-Yamio's theory. So they can be viewed as D-brane dynamics. For example, the BFSS matrix model can be interpreted as D0 brane dynamics, and the IKKT model can be viewed as the instanton dynamics. Okay, so now in this framework, we'd like to see the emergence of geometries for space-time and gravitational theory. And in order to do that, there are some ways to attack this problem. And one of them is the gauge gravity duality. Well, many people think that the gauge gravity duality as the non-perturbative formulation of string theory, and this could be the non-perturbative formulation of string theory, but I'd like to consider the gauge gravity duality as installed duality in the matrix model, because the gauge gravity duality is considered as a duality concerning D-branes or M-branes. So, and in the matrix model, we have D-brane configuration. So these two concepts are, they are, along with each other. So it's natural to think the gauge gravity duality as a part of the matrix model. So let's consider in that way. So for now, And in the gauge quality duality, it is the duality between states in the gauge theory and gravitational theory around the solution in supergravity or just gravitational theory. And these two are the examples of the gauge quality duality in the matrix model. And for example, the BFS matrix model, which is one-dimensional supernomial theory, can be viewed as black zero-brane solutions by taking appropriate limit. So thermal states in the BFSS model correspond to non-extremal black zero-brane solutions. And another example I'd like to tell you is the BMN matrix model, which is a mass deformation of the BFSS matrix model, in which the supersymmetry is, all of the supersymmetry is preserved. So the BMN matrix model has 32 supercharges preserved. And in this matrix model, there are many vacua, and thanks to the supersymmetry, all are just vacua, and the effective potential is not lived up due to the effective, well, potential or something. So we have many vacua in the BMN matrix model, and each vacuum corresponds to a certain bubbling geometry, which is called Limmadosena bubbling geometry. And so this picture is to explain these concepts. So in order to make it simple, I'd like to explain this figure by using the BMN matrix model. So in the BMN matrix model, there are 2 branes and 5 branes. Or more specifically, in the 2A picture, we have D2 branes and NS5 branes. And each vacuum corresponds to a mixture of D2 branes and NS5 branes. And the Limmadosena geometry corresponds to a solution which has 2 brane and 5 brane charges corresponding to that configuration. And the vacuum in the BMN matrix model can be expressed by the fuzzy spheres, so that 2 branes can be viewed as blown up D0 branes, and these blown up D0 branes are, well, in the limit, it is considered as D2 branes, so that if we have infinitely many D2 branes, then that produces very strong gravitational field, and that is the gravity side. And on the other hand, we have open strings on D branes. So, and these D branes correspond to blown up D0 branes, so that we have gauge theory around a certain vacuum. And if we consider, and these D branes are BPS objects. So if we want to reproduce this picture, then we need to consider a certain proper BPS operator. And by I'm not gonna go deep down into this sort of thing, but by considering a BPS operator, a certain BPS operator, we can reproduce the geometry of branes. For example, for the M2 branes, we can reconstruct 2 spheres, and for M5 branes, we can reconstruct 5 spheres by taking an appropriate limit. And at the same time, the same BPS operator can describe the eigenvalue distribution of the BPS operator satisfies the Einstein equation on the gravity side. So at least in the BMI matrix model, it is well controlled by the mass deformation. Well, thanks to the mass deformation. So we have more or less clear, concrete understanding of the realization of geometries of d-branes and gravitational solutions. But still, it is not complete. So, the duality is, as I explained, it is natural to consider the duality in the context of the matrix model, but still, the concrete identification of the degrees of freedom of matrices is, it's still obscure. It's still not completely understood yet. So even though, a BPS operator corresponding to the geometry is identified, the concrete realization of metrics or the, fuzzy, the viewpoint of fuzzy geometry is not understood completely yet. So this direction, in this direction, there are many things to do, and many things to do. And another point I'd like to note is that, the gauge-quality duality is a good concept to pursue the emergence of geometry and gravity, but in the case of the IKKT matrix model, it is not easy to consider the duality, which have been pointed out when the IKKT model was introduced in the past. But considering that the picture is well installed in the matrix model, and also that the matrix model has d-brane solution, d-branes as classical solutions, there should be the duality of blown-up instantons in the IKKT model, but I'm not gonna discuss further in this talk. And more importantly, the thing I like to note here the most is that the dynamics of the emergence is not directly obtained in this framework, gauge-quality duality. So in order to discuss the dynamics, we need to go beyond good symmetries. While in the gauge-quality duality, we make the most of good symmetries. For example, the BMI matrix model has SU2/4 supersymmetry, which is which has 16 supercharges plus more. And so in order to discuss something beyond just the emergence of geometry, we need to do something different from this framework. Now, another direction of the emergence of geometry and gravity is to consider matrix identification of gravity. So by matrix identification of gravity, I mean that matrices can be viewed as metrics or the frame on a manifold. So, and one of this direction is Nada-Kawai-Kimura interpretation, which interprets matrices by the covariant derivative. But the covariant derivatives are, well, vector, has a vector representation. So in order to interpret that as endomorphism in the theory, in the matrix model, we need to do something well, we need some modification for the covariant derivative. And the answer is using the regular representation of spin d minus 1, 1. So this is, well, this tensor product is the key feature to make the interpretation valid. So we have covariant derivative, which has vector representation. And if we act on regular representation, which is labeled by group element of the spin group, well, I denoted by G here. So if we consider a tensor product of them, then that can be written by a direct sum of the regular representation spaces. And this holds for not only for vector representation spaces, but for all representation spaces. And by using this identity, we can use by using the Clebsch-Gordon coefficient of this tensor product, we can construct endomorphism of the covariant derivative in this way. So this R is the Clebsch-Gordon coefficient of this tensor product. So what is good in this direction is that Einstein's equations can be obtained as equations of motion of the Euclidean model. And remark is that we can consider quantum loops in this interpretation, and we can compute effective actions in this interpretation. And if we do that, it's very difficult to do in a precise way, but the structure is uniform, so that we can say the form of the effective action, and it is multilocal. So multilocal effective action is written like this. So it's a sum of product of local action or local interactions. So it has a multilocal form, and this leads to a great scenario of regarding the emergence of standard model or such kind of things, because if we consider such a weight in the theory, then we can compute the Fourier transform of this function so that we can obtain this type of weight. So the multilocal effective action can be rewritten by local action with coupling constants, which are governed by a factor, which is a Fourier transformation of the original weight. So if we can, well, obtain this factor, then we can see how the coupling constants are determined, and that is a scenario to solve the naturalness problem. So, but a drawback in this interpretation is that in order to make this regular representation trick valid, we cannot make a cutoff in this matrix model, so that the dimension of matrices are infinite. So, well, another interpretation is Harold's Weizenbeck connection interpretation in the context of matrix geometry. this provides a finite dimensional matrices, and well, since this is in the context of matrix geometry, we consider endomorphism, which is equivalent to a function space on the manifold, almost locally, which means up to some cutoff of the non-commutative parameters. And on that non-commutative geometry, we consider fluctuation of gravity, and we can identify the frame or the metric of the, well, I should say the frame of the geometry by using this identification. So the commutator can be viewed as the Poisson bracket on the function space, and that can be well, interpreted as the frame. Well, this nabla W, nabla Weissenberg connection, is related with the frame in this way. So by considering this interpretation, we can obtain the, well, gravity equations as equation motion of IKKT model in the very similar way to Hanada Kawai Kimura interpretation. Well, actually, essentially, the essential mathematical structure are the same. And the remark is that, as I said before, in this interpretation, the matrix size is finite. And it is discussed that the ghost modes are absent in this interpretation. So, well, this is also a nice interpretation to read off gravity from the matrices.
Sorry to interrupt.
And
just you know that you have 3 more minutes.
Oh, all right. Oh, thank you very much. I have used up many things in very basic structures, but so considering that mathematical structure is are the same in these two interpretations, well, these two approaches would capture the essence of gravitational identification. Well, another thing is to get something of the emergent geometry and gravity is numerical simulations. And in the context of the gauge-gravity duality, there are plenty of numerical checks of these matrix models. For example, in the BFSS matrix model, the energy, the predicted energy was obtained, including alpha prime and 1/n corrections in a very good manner. And other matrix models are checked in the context of the gauge-gravity duality. So if we want to pursue in this direction, then these are the one to, well, there are many things to do still, but well, it's still going very well. And well, actually, the thing relevant to this talk is this SSD spontaneously symmetry breaking in the IKKT matrix model. So, well, this has been discussed by Nishimura-san in a very good manner. So I need to skip this slide, but well, there is a history of this project, and well, recently the complex Langevin method seems to be working well. So, well, we are about to see the emergence of geometry in a genuine way in the context of numerical simulations. So I'd like to, well, see the problems as, well, see the problems to solve as, well, these two directions. But one of them is the dynamics of emergent geometry and the gravity in the, well, relating with the SSP of the IKKT matrix model. So since the IKKT matrix model simulation is going well, it would be nice to consider the BFS matrix model, which should be related with the IKKT matrix model, probably as a, well, so many people believe that the BFS matrix model can be well, realized in a way in the IKKT matrix model. So by comparing these two matrix models, maybe we can discuss something in this, the relationship between the BFSS and IKKT model. And another thing to discuss, well, I don't have that time, so I'm gonna briefly say about the relationship to the importance of the relationship to the perturbative string theory. Well, since the direction we have seen is a bit far from the perturbative string theory, so well, it would be better to pursue this direction because, well, even though the extensive test of the perturbative string, the correspondence between the perturbative string theory and matrix model has been conducted, it's still not precise and in a well, satisfactory manner, because we need to take some limits for the comparison. So another direction is to reproduce scattering amplitudes in the perturbation theory from all loop correction of the matrix model, because the one loop correction in the matrix model doesn't directly correspond to the one loop in perturbative string. Okay, so well, since I don't have time to discuss, well, I like to briefly show some results, but well, this is not quite very well. So since this is not a good, not amazing, well, it's not really good results I put towards the real-time simulations of the BFS model, but I consider the well, bosonic BFS model and perform numerical simulations for the real-time dynamics for the pure state written by this. So but under this condition, well, it doesn't seem to have SO9 symmetry breaking. Maybe the matrix size is too small to consider. Now, probably, I don't have much time left, right? So, okay, so.
If you could summarize maybe the result.
Yeah, of course. Yeah, so, all right, now, well, in summary, well, what I wanted to convey was we need more numerical simulations to deal with the emergence of space-time and gravitational theory to attack this problem even analytically way. And it seems that recent numerical computation methods are very well and have a potential to check much more of the well, some matrix model features. And I have used the complex Langevin method, but it seems that as explained by Fukuma-san in the first talk in this session, generalized, well, thimble method with a parallel tempering and hybrid Monte Carlo. That's why the volume approach seems to be very promising, and probably need to consider this method to attack this problem. Okay, so I'm sorry for taking much time for my talks.
Thank you.
I'd like to get
any questions? Any question?
Hi, this is Harold.
Hi.
I like very much that you emphasize that you want to compare the BFSS and the IKKT model. And I guess one of the attractive features of the BFSS is that it's easier to understand the time evolution maybe on a computer. Do you see any way of somehow numerically getting access to time evolution in the IKKT model beyond what has been done so far?
Well, yeah, that was kind of my point exactly. Well, in order to, well, of course, the interpretation of time in the work of Nishimura-san and his collaborators is a way to think about the time evolution, but it's still a bit difficult to accept the time evolution. Well, the complexity of the time evolution in the IKKT matrix model. So, in order to understand what is in order to understand the time more, I have been considering the BFSS matrix model. So by considering and calculating the BFSS matrix model and related one-dimensional matrix model, well, I hope the understanding of time will proceed.
That would be good.
Well, yeah.
Any other questions? Okay, so let's thank the speaker again.
Thank you very much.
And this concludes the session. So we start again at 2 o'clock.